In this video, we're going to explore a type of reactions known as oxidation-reduction reactions. In this example, the thermite reaction, iron 3 oxide reacted with aluminum will produce solid iron metal and aluminum oxide. During the course of this reaction, our oxidation number on iron goes from a value of +3 to 0. And our oxidation number on aluminum goes from a value of 0 to +3. In oxidation-reduction reactions, also known by their abbreviation Redox reactions, electrons are transferred between reactants. The reactant that is oxidized, that undergoes oxidation, loses electrons, while the reactant that undergoes reduction gains electrons. There are a couple of different ways to remember this. One way is using Leo the lion goes grrr. Losing electrons is oxidation. Gaining electrons is reduction. Another easy way to remember this is using oil rig. Oxidation is loss. Reduction is gain. And so let's take a look at what this really means. In this example here, we have solid calcium metal reacting with H+, an acid, to then form the calcium 2+ ion in an aqueous solution, and H2, which would be a gas. We're going to learn how to find out the oxidation numbers in just a minute, but in this example, calcium starts with an oxidation number of 0. The hydrogen starts with an oxidation number of +1. In the products, calcium now has an oxidation number of +2, whereas hydrogen now has an oxidation number of 0. Calcium, which had no net charge to begin with, is said to be oxidized, as it now has a charge of +2 in the products. It had to lose electrons, remember electrons are negatively charged, to go from a 0 to a +2. Likewise, hydrogen, going from a +1 to a 0, had to have gained electrons. It is becoming less positive or more negative, either way you want to look at it. But in going from a +1 to 0, we can see that hydrogen had to gain electrons, therefore it is reduced. In an oxidation-reduction reaction, when one reactant loses electrons, another reactant in the reaction must gain those electrons. The oxidation of one substance is always going to be accompanied by the reduction of another, as the electrons are transferred between the two reactants. In order to identify the reactants which have been oxidized or reduced in a reaction, or to even know if a redox reaction has occurred, we must be able to identify the oxidation numbers of all reactants and products in a reaction. To do so, we will use the following sets of rules. We'll go through these one by one. Any atom in its pure elemental form has an oxidation number of 0. And so something like calcium, solid, will have an oxidation number of 0, as that is the elemental form of the metal. Likewise, any other metals in their solid form will have oxidation numbers of 0. Our diatomic gases, which we've talked about, things like H2, O2, F2, I2, Br2, N2, and so on. If these are all in their gaseous state, then they are all in their elemental form, and thus all have oxidation numbers equal to 0. And so absolutely any element in its pure elemental form, we assign oxidation numbers of 0. For any monatomic ions, the oxidation number is going to simply be equal to the charge on that ion. So a calcium 2+ ion is going to have an oxidation number of +2. A fluoride 1- ion will have an oxidation number of -1. If we have the compound iron 3 chloride, then we can see that the iron is going to have a +3 charge and therefore an oxidation number of +3, while the chloride ion will have a charge of -1 and therefore an oxidation number of -1. And so again, for any monatomic ion, the oxidation number will simply be equal to whatever charge is on that ion. Fluorine is going to be fairly simple for us to figure out. Anytime that fluorine is combined with another element, it will always have an oxidation number of -1. The oxidation number of oxygen is always going to be -2 if it is not in its pure elemental form. Remember, anything in its elemental form has an oxidation number of 0. And so O2 in the gas phase will have an oxidation number of 0. Any other time that oxygen is in a compound, it is going to have an oxidation number of -2, however. That is something that will be helpful for us in figuring out the oxidation numbers of other elements that may be combined with oxygen. Just like fluorine, actually all halogens will have oxidation numbers of -1 when combined with other elements. The oxidation number of hydrogen will always be +1 when combined with other elements. And finally, the sum of oxidation numbers for all atoms in a neutral compound must be 0. In a polyatomic ion, the sum must be equal to the ionic charge. And so looking at an example, if we have the compound iron 2 oxide, FeO, we know from our rules that the oxidation number on oxygen must be a -2. We also know from our rules that for a monatomic ion, the oxidation number is equal to the charge on the ion. The charge on the ion for iron must be a +2. And if we look at Rule 7, the sum of oxidation numbers in a neutral compound must be 0. And so we see that works out. In a polyatomic ion, the sum of our charges must be equal to the charge on the ion. For example, our phosphate polyatomic ion, PO4 3-. We know from our rules that the oxidation number of oxygen is going to be -2. We have 4 oxygens. We know that our sum must add up to -3, which is our charge on the ion. Therefore, -8 plus our charge on phosphorus must equal a -3, which means that our oxidation number on phosphorus must be +5. It is important to note here that oxidation number is not the same thing as the charge on an ion. We can see in many cases, such as looking at Rule 2, that they will be equal to each other. However, oxidation number is not the same as the charge on an ion. In both cases, they're more like bookkeeping methods that we use to keep track of electrons in a reaction and what might be happening and where they're going. But oxidation number and charge are not the same exact thing. So let's apply our rules here and find the oxidation number of sulfur in each of the following species. We can see here in the first one hydrogen sulfide, that we have a covalent molecule, and so we can't use our rules applying to ionic charges, but we do know a rule that says hydrogen is always going to be an oxidation number of +1. We do have 2 hydrogens for a total oxidation number of +2 from our hydrogens, and then plus our oxidation number of sulfur is going to have to be equal to 0 since this is a neutral compound. Therefore, our oxidation number on sulfur has to be -2. In our next example, we again have a covalent molecule. We know from our rules that our charge on all of our halogens is always going to be a -1. And once again, we have 2 -1s for a total oxidation number from chlorine of -2. And again, -2 plus our oxidation number of sulfur will have to equal 0 since this is a neutral compound. And so in this case, our oxidation number on sulfur has to actually be +2. Now down here in our third example, we do have an ionic compound of sodium sulfite, and we're going to use that information just to see that we have in fact the sulfite polyatomic ion, SO3 2-. And so now we can use our other rules. We know that the oxidation number on oxygen is -2, and now we have 3 of those -2s for a total oxidation number from oxygen of -6. Plus our oxidation number on sulfur must now be equal to -2, which is our charge on this polyatomic ion. And so in this case, our oxidation number on sulfur must be a +4. And finally, at the bottom, we have sulfur tetraoxide, another covalent compound. Our oxidation number on oxygen is -2. We have 4 oxygens for a total of -8 from our oxygen atoms. Plus our sulfur has to equal 0. This is a neutral compound. And so we can see that our oxidation number on sulfur in this case must actually be +8. And so in our first example, an oxidation number on sulfur of -2. In our second example, oxidation number of sulfur of a +2. Our third example, sulfur has an oxidation number of +4. And in our last example, sulfur has an oxidation number of +8. And so we can see that we have very, very different oxidation numbers depending on what sulfur is actually paired up with in the compound. And so remember that this is not the same thing as the charge on sulfur, because we know the charge on sulfur when it is in an ion form is going to be -2. Oxidation number is different from the charge, as we can see here, with very different numbers for our sulfur oxidation numbers. So let's look at an example of a redox reaction and what's actually happening with the oxidation numbers in our reaction. We can see initially that we have 2 silver plus ions, and so our oxidation number on silver is going to be +1 since it's a monatomic ion. Copper is going to have an oxidation number of 0 since it's in its elemental form. On the product side, silver now has an oxidation number of 0 as it is in its elemental form, whereas copper is now a monatomic ion with a charge of +2, and so it will have an oxidation number of +2. And so we can see here that copper going from its oxidation number of 0 to +2, must be losing electrons. Since it is losing electrons, if we remember our acronyms, LEO goes GER, or oil rig, we can see that losing electrons is oxidation, therefore copper is being oxidized. Now when copper is losing its electrons, silver is then gaining those electrons. Silver is going from an oxidation number of +1 to an oxidation number of 0. Therefore, it is being reduced. And so we once again see that give and take we were talking about earlier, where one species in the reaction is losing electrons, in this case copper loses its electrons to become oxidized, but those electrons must be picked up by something else in the reaction. In this case, silver is gaining the electrons and being reduced. We can also think about redox reactions as far as what an atom is actually doing to something else. So in this case, silver, which is being reduced, is also acting as the oxidizing agent. Silver is causing copper to become oxidized. Therefore, silver is an oxidizing agent. Likewise, copper, which is itself being oxidized, acts as the reducing agent on silver. Copper causes silver to become oxidized. And so the species that is being reduced in a reaction is also the oxidizing agent. Likewise, the species that is being oxidized in a reaction is acting as the reducing agent. And so now try some on your own. In each of these reactions, identify the species being reduced, the species being oxidized, and identify what is acting as the reducing agent and the oxidizing agent. Pause the video now, practice these, and then start the video back up to check your answers. Okay, let's go through them now. And so in our first example, magnesium is in its elemental form with an oxidation number of 0. We know that chlorine is going to have an oxidation number of -1. Therefore, nickel must have an oxidation number of +2. On the product side, once again, chlorine with its -1 oxidation number means that now magnesium must have an oxidation number of +2. Nickel is now in its elemental state, and so we'll have an oxidation number of 0. And so the first thing we see is magnesium going from a 0 oxidation number to a +2 oxidation number. And so magnesium had to have lost electrons. Remember our acronyms. LEO goes GER, or oil rig. And so magnesium had to have lost electrons. Therefore, magnesium was oxidized. Nickel goes from a +2 to a 0. Therefore, nickel had to have gained electrons, and so nickel was reduced. Since magnesium was oxidized and caused nickel to be reduced, magnesium is our reducing agent. Likewise, nickel was reduced, caused magnesium to be oxidized. Therefore, nickel is our oxidizing agent. In our second example, our rules tell us that hydrogen is always going to be a +1. We have 4 hydrogens for a total of +4. We have 2 carbons, therefore each carbon must have an oxidation number of -2. Oxygen is its elemental state as a diatomic in the gas form, therefore has an oxidation number of 0 here in the reactants. Now in our product side, oxygen now will have an oxidation number of -2 since it is in another compound, giving a total oxidation number from oxygen of -4. Therefore, in this case, carbon must now have an oxidation number of +4. Hydrogen is still going to have an oxidation number of +1, and oxygen here will have an oxidation number of -2. And so we can see that carbon, going from a -2 to a +4, had to have lost electrons, and therefore carbon was oxidized. Likewise, oxygen goes from a 0 oxidation number to -2 for an oxidation number. Therefore, oxygen had to have gained electrons, and so oxygen was reduced. And so, since carbon was oxidized and caused oxygen to be reduced, carbon was also our reducing agent. And likewise, oxygen was reduced, causing carbon to become oxidized. Therefore, oxygen is our oxidizing agent. Try this last example on your own without any assistance. Pause the video now if you have not tried it already. Start the video back up to check your answer. Don't worry if this one gave you a little bit of trouble. As you can see, it has to mathematically work out that the oxidation number on sulfur is 2.5 in the products. As sulfur goes from a +2 to a +2.5, we can see that it lost some electrons somewhere. Therefore, sulfur was oxidized and acted as the reducing agent. Iodine goes from a 0 to a -1 oxidation number. Therefore, iodine was reduced and acted as the oxidizing agent. Like I said, don't feel bad if this one did give you some trouble because of that 2.5 oxidation number from sulfur. Oxidation numbers do have to be whole numbers. However, we do get a fraction on this example just because of how the S4O6 ion is arranged. When we look at how all of the atoms are attached in this ion, we have 2 sulfurs central, and then 2 sulfurs on the outside where the oxygens are actually attached. In this example, the 2 sulfurs in the middle actually have oxidation numbers of 0, whereas our sulfurs on the ends have oxidation numbers of +5, which gives us an average oxidation number of all sulfurs of 2.5. This is definitely far advanced from where I would expect you to be at this point, so don't worry if you missed this one. You are never going to see something like this on a test. This is just a little taste of things that are yet to come in your chemistry careers. I hope this video has been helpful in looking at redox reactions and how to classify species in a redox reaction as either being oxidized or reduced, and identifying the reducing and oxidizing agents. As always, if you need more assistance, please feel free to come see me for help, or go to the Learning Commons and see a tutor.